Okay, I think we're ready to start the last talk of the afternoon. So we have Yue Zhang from UC Berkeley about applications of GUTs on minimal volumes of hyperbolic manifolds and sufficiently long Dehn fillings.
Thanks for the introduction. Also, thanks for the invitation to IM. I'm Yue Zhang. I graduated from UC Berkeley. This is the joint work with Ian Agol, my advisor. Most of the results are covered in my PhD thesis. So let's get started. All right. So this talk will cover two topics. The first one is the minimal volumes of hyperbolic manifolds. It's related to the three cusp hyperbolic manifolds, and the second one is about sufficient long dependence, which like related to the norm and also some top sutured manifolds. Yeah. So the first one, Jungsen and Thurston, they proved that the volumes of hyperbolic manifolds are well ordered, and its ordinal type is omega to omega. Moreover, if a volume is of order type omega to n, then there is a corresponding minimal volume hyperbolic manifold with precisely n cusps. So it's very natural to ask the question, right? Like, what's the minimal volume of orientable hyperbolic manifolds with n cusps? And when n is 0, which means it's a closed manifold, Kabay, Manifold, and Malay, they found the smallest volume orientable hyperbolic manifold to be the Weeks manifold, and its volume is 0.94, and it's a closed hyperbolic manifold obtained by 5.2 and 5.1 surgeries on the right hand thing. And then when n equals to 1, Tau and Manifold show that the figure is not complement, and another manifold have the minimal volume, and the volume is 2.02, which is 2v3, and v3 is the volume of the ideal regular tetrahedron. These are very classic results. And then Ian Agol found that like the minimum volume hyperbolic manifold with two cusps, and these two, the y-hat link complement and the -238 parallel link complement are the only minimal volume orientable hyperbolic manifold with two cusps. And its volume is V8, which is the volume of a regular ideal octahedron in hyperbolic space. And he used some technology called GUTs. It's called GUTs, but it's different from what Ian talked in his previous lecture. So in order to distinguish this, I will call them pair GUTs, which come from pair manifolds defined by Thurston. And the GUTs for sutured manifolds, we call them sutured GUTs, but they are kind of related. I will show you later. And now Yoshida found the answer for n equals to 4 using some similar technology of pair GUTs, pair manifolds to estimate volume. And now, like you may ask, like, what about n equals to 3, right? What is the minimum volume with 3 cusps? And there is a conjecture showing that the minimum volume of 3 cusp orientable hyperbolic manifold is the volume of the 3 chain link complement, which is 5.333. 5.33. And
is part of the conjecture that that's the only minimizer?
I think so, yeah. Up to isotropy. So we prove partial result of this conjecture limited to the libroid case. I will define what is libroid later. But yeah, I think this is like half of the progress, and one only needs to show that its logical GUTs has the minimum volume. But I'll show it later. So let's get to some definitions first. Ian already defined the GUTs, the sutured manifolds, and this is just a recap. Like when you have a sutured manifold, you decompose the sutured manifold along a maximal collection of product analyte and product disks This is JSA decomposition. And then you will have some window, which is some product suture manifold. And then you have some guts, which are not product suture. And the guts are the complexity of the manifold, right? Because product suture manifold are trivial. And we are trying to kind of do the exchange of guts to create some more complicated guts to estimate the volume of the hyperbolic manifold. And also this is the same definition of what Ian said in his previous session. So just skip it. And this is a schema of what I imagine the guts of a manifold created to a second homology class. So when you have a second homology class, you take the Farsi surface, which is the maximal collection of system non-minimizing surface representing the homology class. So it's 0, 1, 0, 1, 0, sigma 1, sigma 2, sigma 3, and sigma 0. And you cut along these surfaces, and you do a further JSA decomposition. So you have a gut for each level. And this is how I imagine the suture guts in my head. And by the theorem that Ian stated, the guts are invariant no matter how you choose the Farsi surfaces. And so if M is a hyperbolic manifold, the types of suture guts are actually can be classified into the following 4 types. So the first one is T times I with a boundary component as a torus component of gamma, and to analyze on the other boundary component as sutures. So this is the guts of the white hat link. And the second one is 2ST, which is a solid torus with 2 non-longitudinal sutures in the boundary, right? If it is longitudinal, then it's a product suture manifold, which is trivial. And this can be obtained from the book of Manifolds. And for ST, which is a solid torus with 4 longitudinal sutures in the boundary. I think Ian also kind of give this example in his talk. And the rest is like the most complicated case, which is an cylindrical top suture manifold, and it's also hyperbolic. And we say that if an element Z in the second homology class group is libroid, if the guts of Z only consists of solid tori and T times I, which only consists of the first 3 types. And we prove the following theorem: let N be an orientable hyperbolic manifold of finite volume with 3 cusps, such that every second homology class is a libroid class. Then the volume of M is greater or equal to 1.5 V8. And when you do the calculation, you find that 1.5 V8 is larger than the volume of the 3 chain link complement. So we kind of rule out a huge portion of the cases. And now only need to consider the remaining case, which is there is an element Z such that the guts of Z contains an cylindrical top suture manifold. And we assume, we kind of conjecture that the minimum volume of an cylindrical top suture manifold is 5.33. And once you prove that, then you can solve the conjecture. And before proving the theorem, we need to introduce some definition about pair manifolds and pair guts. And you can see how pair guts and suture gut interplay with each other. So the notion of a pair manifold was defined by Thurston, and you can it's like a pair. It's similar to suture manifold, but it just don't have R plus and I minus. I think of the way I think of pair manifold is like the non-orientable version of sutured manifold. So you just have you just decompose the boundary of M into two parts, right? Like P is a union of essential aniline and toroid, and the rest are some like more complicated surface. And they satisfy like two conditions, like every abelian non-cyclic subgroup of phi 1n is peripheral with respect to P, and every map phi S1 times I, S1 times partial I to N P that is injected on the fundamental groups becomes into P. And the Thurston generalization theorem show that if NP is an oriented pair through manifold with non-empty boundary, then there exists a geometrically finite uniformization of NP. And the term uniformization means that there is a hyperbolic manifold N such that N is homomorphic to the interior of M, and its parabolic subgroups correspond to D. You can it's just classic hyperbolic geometry, so I'll just skip. And like it seems complicated, but I would say like it's not very related to what we do, but just some background. Yeah. So we can define the pair guts, right? So let's say you have a paired manifold, and you let A be the union of a maximal collection of essential aniline whose boundary is on the partial 0 M. So here you notice the difference. When you define the suture guts, you require the aniline to sit one side of the boundary to sit on R plus and the other side of the boundary to sit on R minus. But here, since you don't define R plus and R minus, so you just let them the boundary of the aniline sit on the partial 0 M. So then you can take the union of non-bundle components with negative Euler characteristic, and the part is called acylindrical. The part is called pair guts. Here's a comparison between pair guts and suture guts. So on the left, so let's assume you have a pair manifold, which is also a suture manifold, and the P is equal to the suture. And then we can show you. I'm going to show you how to obtain the pair guts from the suture guts. Right. So first, how to get the suture guts? You just do the maximal collection of product aniline. So which means whose boundary sits on R plus and R minus. And then you only need to consider the extra aniline whose boundary sits both of whose boundary sits on R plus or R minus. And then you do a further decomposition. And then some of this, like this one and this one, they're just I bundle, so you throw them away. And the rest are pair guts. Does anyone has a question about pair guts and suture guts?
So after decomposition, is that possible to generate some more components of paired guts?
You mean like decompose the suture guts into two pair guts? Yeah, that's possible. Okay. All right, and so why do we care about pair guts? It's because like when you have a pair gut, you can have some volume estimation for the pair guts. So Miyamoto says like if N is a hyperbolic manifold with total geodesic boundary, also the pair gut has a total geodesic boundary, then the volume of that hyperbolic manifold is greater or equal than to V8 times the Euler characteristic of N. And because usually like the Euler characteristic of N is less than 0, so you can at least have like some positive bound. And then we have a further result saying that if you have a surface S inside M, and then you can define the pair guts of M and S be like you cut M along S, and then you take the guts of the remaining pair manifold. Then the volume of the original manifold M is greater or equal to the volume of the guts of S. And then if you can get a lower bound for the volume of the guts, then you can get a lower bound of the volume of the original manifold. All right. And so here's what I just mentioned before. Like people conjecture that the free chain link complement is the minimal volume, has a minimal volume. And if you cut the puncture superior here, you can have this kind of acylindrical pair manifold, but it's also a sutured manifold because you can just cut along the surface, so you can have R plus and I minus naturally. And this volume is 5.33. So we conjecture that like this is the minimum volume acylindrical top sutured manifold. And if you prove that, then you prove the conjecture. I will just briefly describe how to use guts to create a pair guts, how to use sutured guts to create a complicated pair guts to add some volume. But this involves a lot of case-by-case analysis. I'll probably just briefly touch it, and yeah, you can check more details in the thesis. So assume Z is libroid, right? And sigma I, the union of sigma I is a facet surface. So then we can have this kind of structure that I have in my mind. And then we say Gi intersect Gi plus 1 if the R plus, so R plus is, so let's say G0 intersect G1 because R plus of G0 intersect R minus of G1. And then we say G1 is disjoint from G2 because this part is disjoint from this part. Let's suppose, and I'm going to show you how to do some operation to create some more complicated guts. I think Ian also mentioned this in his talk. So let's say assume G0 does not intersect G1, right? Then you can kind of move G1 to the top, G0 to the bottom. How do you do that? You just take the surface like this. So original like the surface is like this, right? This is sigma 1, and then you kind of change this one to this to the bottom, and change this part to the top. You have this new yellow surface sigma 1 prime, and you just if you push this back, you have you still have sigma 1 prime, but now you exchange you move G1 to the top and G0 to the bottom. And similarly, you can do the same, right? You exchange G0 with G2 if G0 does not intersect G2. So you may ask, like, can we repeat this operation forever, right? Can we like exchange G0 with G1 and then exchange G0 with G2 with G3 and then move back to G1, G2, G3? And the answer is no. So we proved a lemma that you can only exchange GI with GI plus 1, like doing this so many times, so that in the last step, GI will intercept the guts that next to it. All right, so we so then like when you have two guts that intercept together, if you remove the the middle surface, then together they can create a more complicated guts. And that guts, so that is a sutured guts, but you can further decompose it a little bit to have a pair guts, and the pair guts will have some very low Euler characteristic surface that that guts the Euler characteristics of that gut will be low, and that can give you some estimation for the volume. So let's prove our main theorem briefly. So first, by using a variation of sutured guts, I'll just skip that here. We're able to show that there exists a vertex of the unit degree of the certain norm, such that the guts of this vertex contains two t times I, or 4st, g and g prime, such that each suture of g and g prime is homologically non-trivial, and each suture of g is not isotopic to any suture of g prime. So you might see like the conditions are very complicated, but we just want to rule out the case that you have a hexagon of times I that Ian mentioned, that you can have two 4st and then you group together, they will have a like you have a 4st here and then you have another 4st here. I just want to rule out this case because this won't give you too much information about the volume. They're like too trivial from my understanding. Yeah, so let's discuss it case by case. So we assume, like, for example, the first case is that you have more than two suture guts components, right? And then so you have G0, G1, and GI. So first, you can exchange G0 with G1, G2 to the end until it intercepts a suture gut, another suture gut component. And without loss of generality, we assume G0 intercepts G1. And we will do the same operation for GI until it intercepts another GJ. Now you have three cases. So first, if this GJ is greater than 1, then you can remove this middle surface and this middle surface. So you just consider sigma 0, sigma 2 prime. So this case, like this only have 4 guts, but you can also think about more guts components. So if you only have 4 guts components, then you just take sigma 0 prime and sigma 2 prime. And so G0, G1 together will become a more complex guts, right? And GI and GJ will together form another complex guts. And you can do a further decomposition to from the suture guts to a pair guts, which does not change the Euler characteristic. And by the theorem that I just mentioned, that the volume of these pair guts will be at least V8, and the volume of these pair guts will be at least V8. So together they will be at least 2 V8, which is greater than 1.5 V8. So we proved this case. So let's assume that if GI intercept G0, right? In this case, you just remove the middle surfaces like sigma 2 and sigma 1. So these 3 guts together, you can prove that the pair guts that contain these 3 guts has Euler characteristic smaller than or equal to -2, and its volume, therefore its volume is greater than 2 V8. We will also prove the statement. And then a more, does anyone has a question? Anyone confused about this? All right. Yeah. So the more tricky part is the case that you only have 2 suture guts components, and So the case one is you have at least one component, which is T times I. In this case, I will going to show you how to do some operation to get another surface that can produce a new pair manifold. So if you have a T times I, then you can take to analyze here, and you do a surgery, right? You just remove this small interval, and then you add these to analyze. So you have this sigma prime. But so I just want to mention this sigma prime is not taught. It's not like, because the orientation on this boundary is they're opposite to each other. But this is allowed when you get a pair manifold. So I have this new sigma prime, and you just cut along. So instead of cut along sigma 0 and sigma 1, now you just cut along sigma prime, and you will have this new pair manifold, right? Like this small curve corresponds to C0, and the rest, the upper curve corresponds to E1 because it goes back to here, right? And the bottom part corresponds to C0, and G1 still remain the same. So then, if E1 is disjoint with G1 and C0, you do the same operation. You just take an analyte and double it, and you kind of remove this small blue interval, and then add these two green analyte to it to have a new sigma prime surface. And then you instead of cutting along sigma prime, you cut along sigma prime. And this is the resulting manifold. So every time you can kind of like, so now you create a new E2 because like this part goes back to here, and it randomly appear on the bottom surface. And if E2 still disjoint with C0 and G1, you do the same operation, and you keep doing it again and again. But because the other characteristic is constant, so you can't do that so many times. And finally, at the stage n, you will have En that either intercept G1 or intercept C0. And now you have this like ideal case that we want to estimate the volume. And you can easily show that the pair gut of this component has Euler characteristic smaller than or equal to -2, and hence the volume of M is at least 2V8. And I hope this case-by-case analysis don't get you lost. And so this is a similar technique that Ian used in his paper to prove the minimum volume of hyperbolic manifold with two cusps. I just want to point out that the inequality is sharp for the Borromean rings complement in this case. Like the volume of Borromean ring is 2V8, and yeah, it's exactly the case that we discussed. So this case, so now you restrict to the case that you only have two sutured gas components, and both of them are for STs, and this is the most difficult case. That's the reason why we only have the lower bound 1.5 V8, not 2 V8. And so we come up with the idea that you just take a double cover of M with respect to the homology class Z, so that you can have G0, G1, and then another copy of G0 and G1. And you do some similar case-by-case analysis. You do the exchange of different gaps, and yeah, you finally can prove that the volume of this double cover is at least 3v8, and hence like the original one is at least 1.5v8. Yeah, so therefore we prove the theorem. So this is the first part. I will just pause here in case you have any questions.
Do you use the uniqueness result that Ian mentioned?
I think we kind of use that in showing that there are at least two. Two, like at least two gas components.
Oh, okay.
And I think that is essential. Yeah, this lemma 16 like contains at least two components such that each suture and G prime is not. Also, Ian also so in the first part of the talk, I think we also kind of like you can have a suture decomposition from low, so like from the vertex to the edge, you can have a suture decomposition for the guts. Like if you have the, let's say this is the system norm, right? And at the vertex, you have a guts corresponding to this one. And for this, for a point on this edge, let's say y, you also have another guts. And we show that. So naturally, you can see that the guts of the z is more complicated than the guts of y, and we show that there is actually a suture decomposition from z to y. And because because the manifold has three cusps, so its homology space is at least three-dimensional. So you can kind of like have this three-dimensional ball. And so from the vertex to the edge, and then from the edge to the face, you have like a non-trivial suture decomposition of that too. And therefore you can kind of come up with this argument that you have at least have two T times I or for SD such that they satisfy the following conditions. All right, so let's move to the second part. Like so we kind of, this part is not very related to the theorems that Ian stated, but it's the same philosophy of guts. Like you try to remove the you try to remove the trivial parts, and you only focus on the non-trivial parts. So I assume everyone is familiar with Dehn filaments, and we want to show that we want to show some properties that satisfy for sufficient long Dehn filaments. So let N be a compact manifold whose boundary is a union of tori, and the Dehn filament coefficient beta I on the ith component of N is either the isotopic class of an essential simple closed curve on the boundary or infinity. So infinity means like you don't fill at all. And given a Dehn filament vector beta, we denote the manifold obtained by this specified Euler by N beta. And here's the definition for sufficient long dependence. So like, like math care about infinity, right? They don't care like how, most mathematicians don't care like, do you have a property that satisfies for 1 or 2 filaments. You actually care about the rest. Like if we remove, if we exclude some finite sets of the slopes on each boundary, does any property satisfy for the rest then filaments? And yeah, so this is the motivation why people care about sufficient long filaments. Like you just exclude some finite sets on each boundary, and you require the difference, the coefficient to be outside of these sets, and but the sets are still infinite, so it's still very interesting to consider. So, for example, Sussman's Dehn surgery theorem shows that all sufficiently long filaments of a hyperbolic manifold are still hyperbolic, and this is very cool. So here comes a very important definition in filaments, at least for sufficient long filaments. So let's say M is a 3 manifold, and the boundary of M is so like partial 0 M is a union of total boundary components. So M can have some other components, but we only consider the total boundary components. And we say M is coannular if there exists an essential annulus whose boundary curves, so it has 2 boundary curves, are essential in distinct components of partial 0 M. And yeah, if it doesn't satisfy the condition, then it's coannular. And why do we need? So in the following talk, we require the manifold to be coannular. And why do we need that? It's because if you have this kind of annulus, then there is a mapping class group corresponding to mapping class groups of Dehn twists along this annulus, and that can produce infinitely many sets of Dehn filling, right? If you have Dehn filling on these 2 boundary, and you just do a Dehn twist, then you have another different set of Dehn fillings, and that can produce infinite, and it will like cover. It will be like an infinite set of slopes on each boundary, and that. So then, like, yeah, we need to remove that to prove property for sufficiently long Dehn fillings. So, and a very important note: a hyperbolic 3 manifold is coannular, and so we kind of in this talk we kind of generalize some properties for hyperbolic to coannular manifolds. So this is the lemma that we use for generalizing many theorems in sufficient long Dehn fillings. So let's say M is a compact orientable irreducible and coannular 3 manifold with only total boundary. And we let beta be the Dehn filling vector for the boundary of M. And N beta is the filling with respect to beta. B beta is the union of solid torus associated to the filling. And we let F is a properly embedded kinetic surface in M beta, which is the resulting manifold from Dehn filling, such that F intercept B beta non-trivially, but we don't require to intercept every B beta, just intercept one component of B beta. And then you can consider F circle, which is the intersection of F and the original manifold M. We require it to be incompressible and partial incompressible. Then for any number of H, we can show that for all sufficient long length lengths, the Euler characteristic of F is smaller than H. And this is very powerful because you show that for any H, you just pick a finite set of slopes, and then excluding those slopes, every surface F has low Euler characteristic, and that means that it's very complex. And this can be used to prove some theorem related to system norm, because system norm cared about the Euler characteristic. Also, you can prove some tautness of a sutured manifold, and yeah, and also even you can prove some theorem related to link complement, and I will show that later.
Do you mean making those exceptions?
Yeah, which one? Like
What is X?
kind
It's
of.
also norm?
It's non-negative. It's what do you mean?
Yeah, what is X?
Which one?
Pi of F is Euler characteristic.
Right. So
You
it's
mean
minus. Yeah, it's from minus infinity to 2.
So H is negative, mostly, yeah.
And then
Yeah,
you
yeah.
say 3
Ah,
will be
okay.
true for any surface.
Yeah, if this is 3, then it's true for every surface. But like for example, if a negative 100, it's still true for all sufficient long filaments.
You can go as negative as you want.
Yeah.
So you put
Increase the
minus
units as much as you want.
minus 1,000 to mean that all surface could be very large.
It can be large, right? Like the Euler characteristic of a sphere is 2, and then torus is 0, and yeah, any hyperbolic space is negative. Yeah. So this lemma actually have some history. So Lee proved this lemma when M is hyperbolic three manifold with boundary as a single torus, so only one torus. So more generally, when the interior of M is a hyperbolic manifold of finite volume, then this lemma can be proved by Gauss-Bonnet theorem and Thurston Dehn series in Lanigan, Linsky, Soto, and Taylor's paper, recent paper. But we use a different method by using zero efficient triangulation. So we don't require the hyperbolicity. And we generalize in an idea of Jacob, Rubinstein, and Sedgwick. We can decompose a normal surface into a sum of fundamental surfaces in a zero efficient triangulation of M. And then, so then every normal surface will be expressed as a sum of these fundamental surfaces. And then because the Dehn slope is huge, right? Because it's NM and NM are pretty high. So that means the sum is pretty big too. And that will produce a very negative value of the Euler characteristic. So that's a basic idea about how to prove this. And I'm going to show so I'm going to show how to apply this method and some other tools to prove a system norm related problem. So let's say if M circle is a compact orientable irreducible through manifold, whose boundary components are tori. So when density are only on a fixed boundary component T, Goodbye showed that for properly means tot actually. Properly non-minimizing surface S circle disjoint with T in N circle. N circle is the original circle, manifold. Then S circle is still properly non-minimizing in the fillet along T for all except at most one slope in T. So that's what Scott just mentioned in the previous talk. And then Seller extended this result by showing that all properly non-minimizing surface is joined with T. So now, like, you come, you improve the theorem from just one to all, and you can show that like they're still properly non-minimizing in all definiteness for all, but except a finite number of slopes, because all properly non-minimizing surfaces are infinite. But now you only need to exclude a finite number of slopes, so it's a better result than combined. Then you may ask another, like, a further question, right? Like, what if the surface intercept the boundary that we're going to then fill? And that is what Baker and Taylor did. They showed that so like some restriction, right? This is some like trivial restriction, like M0 circle is not a product of torus, and an interval it's not a torus times interval or a cable space. Then for a slope beta on T, we let S circle be a properly non-minimized surface in N, such that S circle meets T in the slope of beta, and we cap off. So in this case, you need to cap off the component of the boundary of S, right? Otherwise, it's not a properly invalid surface in the resulting manifold from definite. So you cap off the components of the boundary on T with this to obtain the surface S. And Baker and Taylor, they show that except a finite number of slopes on T, each such S is properly non-minimizing in the definite. So if you like set it in a sufficient long definite, so that means they show that each S is properly non-minimizing for sufficient long definite. And a very natural further question is asked, can we, so all of them only consider one boundary component. And what if people want to then fill two components, right? Or like three boundary components? What would happen? And by using the key lemma, we prove that for multiple components, then this argument is still true. So, but you need to require the manifold to be equiannular. I already stated the reason, and the other condition are trivial. So then you let beta be a definite vector for M circle, and S circle is a properly non-minimizing surface in M circle, such that each component of the boundary of S circle means the boundary of M circle is of slope beta I. If beta I is non-infinity, that means if you have a dampening on one boundary and the surface intersect the boundary, then the intersection should be of the slope of the dampener. And then you cap off the components of the boundary of S circle related to the dampener with this. So you have a new surface S beta. Then for sufficient long beta, S beta is a properly non-minimizing surface. And I think we use this method is different from what Baker and Taylor did use, and I think it's more powerful, say, because it can be used for multiple components. And the basic idea is so we use hot normal surfaces, Grant surfaces, zero efficient triangulation, and a key lemma to prove it. So we fix a zero efficient triangulation T. And we show that there is a finite collection B1 to Bn of top homology IBS, which means rivulous incompressible Grant surfaces in M circle. And such that for each second homology class, there exists a properly non-minimizing surface of the class that fully carried by one of the RIBs of the collection up to isotopy. So I know I introduced a lot of terminology. Are you familiar with branch surface? So okay, so I probably will skip that. And the way I think of rivulets and compressible, I think of them as also top. Like they just sound like I probably don't want to confuse it too much. I just think of them as some top branch surface, and we are not going to use a lot of the properties of these IIVs, so it's okay. Just think of them as top branch surface. And fully carried mean that each so branch surface like this, right? So fully carried means the surface will touch each foliation, a vibration of the branch surface. And the reason why we want to have this finite collection is that because it's finite, so you only need to prove the theorem for surfaces fully carried by each BI separate. And that kind of transforms the problem from infinite to finite, because the surfaces that fully carried by branch surface, they look like the same when you decompose the surface, when you decompose the manifold along the surface. So then you only need to consider each branch surface PI separately. I think that's like a key step to show to prove the theorem for sufficient long difference. So on the left, you kind of so the gray area. So we assume S circle is fully carried by one of the IVs B, and the gray area in the left figure is the fiber neighborhood of the branch surface, and X is the complement, and S circle is the blue curve. So you can see it's fully carried by this branch surface. And we are going to show that the guts of this S circle is contained only in X. So kind of like trying to decompose manifold, sutured manifold into two parts, which are trivial part and non-trivial part. So first, this is a standard operation from WMST's paper and also like previous normal surface paper. You thicken S circle to have an I bundle, and then you isotope the I bundle to touch the boundary, the horizontal boundary of X, right? So you move the top one to touch the top X, and you move the bottom one to touch the bottom X, and so that like so that the boundary of this neighborhood will contain the horizontal boundary of X as well as of X. Sorry, this is the type of X, and then you just replace S circle with the boundary of this neighborhood. It just double it because it's a island, so it doesn't change anything about the property of S circle. So we just for simplicity we just consider S circle to be the boundary of this neighborhood, and then you can do a suture decomposition for M along S circle, and you can obtain a top suture manifold, which is F, and then you can you can see that X can actually be obtained from f by cutting along some product line, right? This vertical line here, they are product line, and if you just cut f along this vertical line, you can have x and the gray area and also the blue area. And so we call the rest like f minus x L. And you can see L is actually a product sutured manifold, which is trivial. And so X contains the guts of S circle. So now we kind of want to show that two things. Let me say the lemma first. So the by show that if you have a sutured decomposition from one sutured manifold to another sutured manifold, that the decomposition is either a product disk or a product annulus, then the original one is taught as if only if the new one is taught. So go back to this slide. So we can show that if X and L are taught, if and only if F are taught. And then the second lemma, we proved the second lemma that if you decompose M along S, and if M minus S is taught, then S is a properly non-minimizing surface. So go back to this one. If so our solution will be we prove X and L are taught. Then by the first lemma, you can show that F is taught. And then by the second lemma, you can show that S circle is taught too. And right. So we want to use this lemma to show that the resulting manifold is still taught, right? So we want, so it's not about the original manifold, it's about the result manifold after the Dehn filling. If we can show that X beta is still taught, so X beta is the result manifold from the Dehn filling, and then no component of the resulting product manifold L beta of L is a disk times an interval. Then if you glue them back, you can show that by using this lemma, you can show this manifold is taught. Because this M beta minus S beta is the resulting manifold F beta of F from the Dehn filling. I think it's confusing, so I need to omit. So you have F, which is M minus S, and then you have X, which are the dot part, and then you have L, which is the product part. So after Dehn filling, you have F beta, you have X beta, you have L beta. So we first show that after the Dehn filling, X beta is taught. And you can also show this is not a disk times interval. This means L beta is also taught. And so you can, by using the lemma 20, you can show F beta is also taught. And because F beta is M beta minus S beta, so by using the second lemma, we can show that S beta is a certain non-minimizing surface, and therefore we prove the theorem. So the only remaining problem is trying to show X beta is taught and L beta is not this times interval. And so this comes from the idea of the key lemma, right? after sufficient long Dehn filling, every surface inside the resulting manifold will have very low Euler characteristic, and it will be lower than the Euler characteristic of R plus and R minus. Therefore, you can't find any smaller system norm for the same homology class. So we can prove that this is tough, and this one is similar. Like you just prove it. This is easier than the first one. And once you use the key lemma to prove these two things, then you can show you can easily get that like S beta is probably non-inline. I probably will skip this. I just want to state another application on links. This is easier to understand. Probably just take 1 minute. And so not complement homological. Once you have a not complement, the corresponding knot is unique up to isotopy. But links are not generally determined by the homomorphism of their complement. The most obvious example comes from twisting along a disk spanning it's an unknotted component of the link, right? And another case is that if L has two components which are spanned by an annulus, you can also do a Dehn twisting along that annulus. And if you have another component of the link that meets this annulus, you will generate a new, completely different link. And but if we exclude these two cases, then we can show that the number of links with a given complement is finite. But we can show that it's one, but we can show that it's finite. So here's some definition. If K1 is a knot with a regular neighborhood eta K1, and K2 is an essential simple closed curve on the boundary of the neighborhood, which is not a meridian of eta K1, then we say K1 and K2 is coaxial. And we let L0 be the set of links such that no component of K is unknotted to exclude the first case. And then no two component of sublink of L is coaxial. And if if you only consider links with this certain restriction, then the number of links is finite. So Gordon stated this in his paper, but then later I found a gap in his proof. I talked to him. He said probably hasn't figured out the way to prove it. And I use my key lemma and some similar technology to prove this. And if you are interested, you can check my thesis. Probably the first part, Ian and I will publish, put it on archive this month, trying to wrap it up. And the second part, once I have more time, I will try to put it on archive too. Thanks.